Okay, I need to upload a file to Blackboard, which has some, I'm going to upload a Mathematica file, which you might use to play around with some of what we're going to do. Give me a sec. Okay, if you look under Mathematica files, you're going to see a new file that I just uploaded. So go ahead and download that if you want. I'll give you a minute to do that. I'll get my other device set up. Okay, so here's what we're going to be doing today. We're going to be talking about Bessel functions, which are solutions to the wave equation in cylindrical coordinates. I'm going to walk through the derivation of Bessel functions. I have no illusions that you will retain every single step of that derivation. The derivation is a mess, and the main reason to walk you through this derivation is so that you get at least vaguely familiar, and then if you really need it in the future, it will be your second exposure as you read through it rather than your first. After that, I'm going to talk about qualitative characteristics of the Bessel functions and qualitative features that really matter for making sense of waves in cylindrical coordinates. All right, so you saw on the homework assignment that if we have this equation, oops. If we have this equation, then we can guess a solution of the form psi equals f of r e to the I kz times z e to the I m phi e to the minus I omega t. And this solution is an eigenfunction of three of the derivatives, meaning that if we take these derivatives, if we take the second derivatives with respect to z or phi or t, we just get the same function back multiplied by a few constants. And if I want this function to be single valued, which means that if I go around the z-axis, start here, go around, get back there, then what can we say about m? E to the I m phi had better be the same if we add 2 pi to phi. So what can we say about m? Anyone?
Has to be an integer.
Pardon?
It has to be an integer.
Yep, has to be an integer. Which is kind of weird for what we're going to do next, because what we're going to do next is actually much easier if m isn't an integer. And so I'm going to start by not assuming that m is an integer and do kind of the easy math, and then point out all the things that actually get weird and difficult if m is an integer, which sadly is what reality requires. So sometimes the unrealistic case is actually easier, which is frankly why theoretical physicists are known to do math in higher or lower dimensions than correspond to reality. They find that a one-dimensional model is easier than a three-dimensional model. Okay, fair enough. So there's a four-dimensional model is easier than a three-dimensional model because certain things blow up in 3 dimensions, but not 4. Anyway, if we plug all of those in, then what you should have found is that we get 1 over r partial by partial r partial f partial r minus kz squared f plus, minus m squared over r squared f equals minus omega squared over c squared f. I might not have put the 1 over c squared in there, but technically we should be doing that. And this equation looks kind of ugly, but there were a few things that we could do. First of all, we could add omega squared over c squared to both sides. And while I'm at it, I'm also going to simplify this derivative. And we get partial squared f by partial r squared plus 1 over r partial f partial r plus omega squared over c squared minus kz squared f minus m squared f over r squared. All of that is 0, which looks ugly, but first of all, we can take this and call it k squared. And then I'm going to define x equals kr. The textbook uses x. I'm reluctantly going along with that. X equals kr. And I could just divide everything by k squared. And I could make this a derivative with respect to kr. And this would just become 1. And finally, I'd be left with the second derivative with respect to x plus 1 over x partial f partial x plus f times 1 minus m squared over x squared equals 0. Any questions on that? This is called the Bessel equation. It's a second-order linear differential equation. And we're going to attempt a power series solution. But this equation has a singularity. And we saw a couple weeks ago that when equations have singularities, then if they have a singularity at x equals 0, we can't just say, hey, it's the sum of a constant plus another constant times x plus another constant times x squared plus another constant times x cubed. We're going to guess instead that f of x equals x to the sigma. Sigma is currently unknown. We're going to figure out what sigma is. Sum from n equals 0 to infinity of an a sub n x to the n. Now that sigma is possibly not an integer and possibly not a positive integer. And that sigma captures the fact that this function might not be completely well behaved. This function might have some singularities. You know, if we have square root of x, you can say, well, square root of x doesn't blow up at x equals 0. No, but the derivative of square root of x blows up. And so we're saying that we can factorize this into something that might have a singularity, if not in its value, then in its first derivative or second derivative or 17th derivative, and something that's nicely well behaved. And if we do that, I can rewrite this as the sum of a sub n x to the n plus sigma, which will make our lives somewhat easier. When we take derivatives, you don't have to use the product rule. So df dx is the sum from n equals 0 to infinity of an n plus sigma x to the n plus sigma minus 1. And the second derivative is the sum from n equals 0 to infinity of n plus sigma n plus sigma minus 1 x to the n plus sigma minus 2. And that's just by the definitions of derivatives for simple powers of x. Now, one thing we can't do that we often do, when we have a derivative, we say, well, okay, this factor of n is 0 when n equals 0, so I could start my summation from 1 and then do some tricks. But we don't know that n plus sigma is 0. And if sigma is 0, then sure, n plus sigma is 0 when n equals 0, but we don't yet know what sigma is equal to. So we can't do that. We have to just leave these summations alone. And if we write all of this out, d squared f by dx squared plus 1 over x df dx. Well, let's see, if I take a 1 over x out in front of this, that's going to be n plus sigma, x to the n plus sigma minus 2. And 1 over x squared times f, we're also going to be subtracting 2 from the exponent. So if I play my cards right and write all of this correctly, and you'll notice I'm writing this out a little bit differently, simply because there are things where we get powers of n plus sigma minus 2, and there are other things where we don't get that power. And I want to separate it out nice and clean. When I put all of that together, I get the sum from n equals 0 to infinity of an times a giant mess, an times n plus sigma minus 1 times n plus sigma plus n plus sigma minus m squared x to the n plus sigma minus 2 plus the sum from n equals 0 to infinity of an x to the n plus sigma. Any questions at this point? Well, let's see. This is going to be n plus sigma times n plus sigma minus n plus sigma. And then I've got a plus n plus sigma, which, hey, those cancel. Minus n squared. And then I'm going to multiply by x to the 2 minus sigma. Multiply everything by that. And now things become a little bit cleaner. Because if I multiply by x to the 2 minus sigma, I add 2 and subtract sigma from each of these exponents. Okay, now we have a series that's much cleaner. Now we have a series where we could start doing some tricks. Because I could rewrite this. I could say, look, the lowest power in here, well, you tell me, what's the lowest power of x?
2, 0.
Oh, really? I have x to the 0 here?
Yeah, it's
plus
2.
2. So I could rewrite this as the sum from n equals 2 to infinity, a sub n minus 2, x to the n. Because the coefficient of x squared is not a sub 2, it's a sub 0. And the coefficient of x to the 4th is not a sub 4, it's a sub 2. Then here's what we do. We set x equal to 0. And the reason why is because, well, we know this equation ought to hold everywhere. It ought to hold for all values of x. But x equals 0 is a particularly easy case to handle. All right? If we set x equals to 0, then all that we've got, like the x to the 1 term, the x to the 2 term, those have to be 0. All powers of x to the n with n greater than or equal to 1 are 0. So we know that at x equals 0, all of the other terms are satisfying this equation. But what about the constant term? All right. Well, let's see here. Does this second summation have x to the 0 in there?
No.
Nope, I don't see x to the 0 in there because it starts with n equals 2. So it's only going to be in here. So we're going to have n plus sigma squared minus m squared a0 x to the 0 equals 0. And well, let's see, n is 0. So that's going to be sigma squared minus m squared a naught equals 0. So sigma is plus or minus m. Any questions on how I did that?
Does that say n is equal to c, or is n is equal to 0?
N equals 0.
Thank
you. Any other questions? Okay, so at this point, we can rewrite this whole thing as the sum from n equals 0 to infinity of n plus m squared minus m squared. You may be thinking, shouldn't that be n plus or minus m? Sure, except that I've got positive values of m and negative values of m. So I'm allowing for both. I don't have to write plus or minus. All right. Actually, I was a little bit sloppy there. Let's not do that. Okay, this has to be true for all powers. Now, we already know that this is true for n equals 0. All right, we already know that this equation is satisfied for n equals 0. For n equals 1, is there an x to the 1 in the second series? Nope, because that index starts from 2. So we're going to have 1 plus m squared minus m squared times a1 x to the 1 equals 0, which is only guaranteed if a1 equals 0. And for n greater than or equal to 2, we're going to have n plus m squared minus m squared times an plus an minus 2 times x to the n equals 0, which only works if this whole mess over here is equal to 0. So we get that an equals minus an minus 2 over n plus m squared minus m squared, or minus an minus 2 over n squared plus 2nm. And you could say, what about the m squared from there? Well, it cancels out that m squared. All right. Any questions on the procedure before we start interpreting? Okay, first of all, we have a recursion relation that gives everything in terms of the term that was 2 before it. So if a1 equals 0, a3 equals 0, a5 equals 0, a7 equals 0, etc. All right, so that's one thing. We know that we only have even values of n. That's nice. Another thing we could ask is, does it converge? Well, the terms are alternating sign and you're getting smaller very rapidly, okay? They're getting smaller very rapidly. If we didn't have this thing in there, okay? Or if we didn't have that in there, it would almost be approaching 0 as 2n factorial. It's 1 over 2n factorial. No, an is not exactly equal to 1 over 2n factorial, but it's approximately that, because every time you go up by 2, you divide by n, and then basically n plus 2m, which is close to, it's of the same order as n plus 1. So we could approximate as dividing by n times n plus 1. It's not exactly, it would be a rough approximation to tell us that, yeah, this thing is going to 0 very rapidly. And so this looks a lot like the series for cosine. It's not actually the series for cosine. If anyone says, a Bessel function is just equal to a cosine function, they're wrong. But the series is going towards zero. The coefficients are going towards zero about as rapidly as the coefficients that go towards zero in a cosine. So it's convergent for all x values. So that's good. We don't have to worry about this series blowing up. And we know that even though there are some complications with integer values of m, we know that there's always at least one series solution. There are two linearly independent solutions, but there's always at least one solution that can be obtained straightforwardly just from going with the recursion relationship that we have. We discussed that 2 weeks ago. There's always at least one solution where you just take the series and you run with it. And then the other solution might be more complicated. So we can say that we're going to call this J sub m of x. J sub m is a Bessel function of the first kind of order m. And then we could say, sorry, an equals, well, if a0 is 1, a2 is going to be, if we just go up to that recursion relationship, it's going to be minus a2 minus 2 over, I'll rewrite this as n times n plus 2m, 2 times 2 plus 2m. A4 will be, so it's going to be a0 minus a0 over 2 times 2 plus 2m. A4 will be, well, we're going to take a2 and multiply it by -1. So we're going to get an a0 over 2 times 2 plus 2m times 1 over 4 times 4 plus 2m. A6, we're going to take the previous thing, multiply it by -1. We're going to get minus a0 over 2 times 2 plus 2m times 4 plus 2m. And then we're going to divide also by, that should be a 6 there, 6 times 6 plus 2m. So these things are decaying very rapidly, all right? And we're not going to, I'm not going to spend a lot of time on writing down formulas for the coefficients. The textbook walks you through formulas for the coefficients, all right? I just want to look at these qualitatively for now. So I'm going to switch to Mathematica. And if we plot Bessel functions of the first kind, here's J0. The Mathematica command for them is just Bessel J, because the first kind of Bessel function is called J. That's just its name. M tells you the order of the Bessel function. X is the variable. I plot it out to 15 for convenience, shows you a lot. M equals 1 looks like that. M equals 2 looks like that. Notice that when M was 0, the value of the Bessel function at x equals 0 was 1. It was a constant. It was non-zero, constant. When M was 1, You see how it's rising linearly at first? When m equals 2, it's rising parabolically. And if m equals 3, it rises initially even more slowly. M equals 4, more slowly still. Although I don't expect you to know all the coefficients, I do expect you to know that the Bessel functions are x to the m times some very messy power series, okay? And so what we're seeing here is x to the 4th, because m equals 4. I'll do a magnification of 200% so it shows up better on your screens in Zoom. We're seeing x to the 4th here. Here, we're seeing x to the 1. Now we'll skip the Bessel functions of the second kind and the modified Bessel functions for a moment. Even though we know that for solutions to the wave equation, m should be an integer, there's nothing in the Bessel equation that requires m to be an integer. We could always plug in half integer and we get something perfectly valid. There's no rule that says it has to be exactly a half integer. I just randomly selected something. I could say m equals 2.71828. There's a solution there. Who knows if we're actually going to use that, but as a mathematical fact, it's valid. Let's look at small x. Let's just verify what I was saying, that these Bessel functions are proportional to x to the m for small m. If they really are proportional to x to the m, then if we took the Bessel function and divided it by x to the m, we should get something that at least initially is flat. And sure enough, we do. The ratio, here I'm plotting in orange, the ratio of jm to x to the m. You can see that at least initially, it's flat. Now it slowly starts to change because it's not exactly equal to x to the m for all values of x. The approximation gets worse, and the coefficient of x to the m might be pretty small. In fact, that coefficient gets really small really fast. If m equals 7, the coefficient of x to the m is 1.5 times 10 to the negative 6. Still, the fact remains that it's flat, so we can say that yes, indeed, it is proportional to x to the m. Any questions so far?
Does a half integer of m have any physical implications, or are we just observing the fact? Because I notice for every half integer, that your Bessel function starts at 0, and so I was curious if there was any physical implications.
Not for that specifically, but there's a coincidence which we might get to on Wednesday, which is that there's another function very similar to the Bessel function called the spherical Bessel function. And the spherical Bessel function is equal to the regular Bessel function with half integer m.
Okay.
Right? There's an interesting coincidence there that if you know the Bessel functions for m equals 1/2 or 3/2 or 5/2 or whatever, then you also know the spherical Bessel functions for L equals 0, 1, 2, 3, 4, 5.
Okay, cool.
There's a whole menagerie of Bessel functions. There are many types of Bessel functions. We're talking about Bessel functions of the first kind. There are Bessel functions of the second kind. I've used them in my research. We'll get to them in a little bit. There are spherical Bessel functions. And among the spherical Bessel functions, there are, again, spherical Bessel functions of the first kind and of the second kind. There have to be two kinds because you have to have two linearly independent solutions. Now, the Bessel functions of the second kind also get called Neumann functions. And then some people say, you know, I'm going to take the Bessel function of the first kind, Jm, and I'm going to add to it the Bessel function of the second kind, which they call usually Ym, although some people call them Nm. I'm going to add them together, and I'm going to call that a Hankel function. And then there are spherical Hankel functions. And then there are modified Bessel functions, which actually turn out to be important for understanding total internal reflection of light in fiber optics. So you've got Bessel functions of two kinds, Hankel functions, Neumann functions, spherical Bessel functions, spherical Hankel functions, modified Bessel functions, modified spherical Bessel functions, modified Hankel functions, modified spherical Hankel functions. It's a bit like, you know, a zoo with like 15 different species of something. You know, it's like you could have a David Attenborough documentary. Here we are observing the Bessel function in its native environment. Now, when a Bessel function meets up with a Neumann function, they can mate in the right season. And in the mating of the Bessel function and the Neumann function comes a Hankel function. Let us turn our attention to the spotted modified Hankel function of the second kind. And I'm not the only person to make jokes about zoos of Bessel functions. There's actually this whole menagerie. Here's the best reference book on Bessel functions. It's called the Nist Library of Mathematical Functions. This has a long history. A long time ago, there was a book called Abramowitz and Stegu. This brown book, one time a pocket book, but it quickly became something other than a pocket book. The Handbook of Mathematical Functions, published by Nist, National Institutes of Standards and Technology, which is actually a major employer of physicists. And Nist has essentially three functions. One is to produce standards. It could be standards for things like weights and measures, you know, defining what exactly is a kilogram, what exactly is a meter to high precision. And those are things that we can all appreciate, but then they'll also get involved in standards for much more specialized things. You know, the odds are good that, and I'm making this up, but I'm sure it's right, that if the government or if a regulator has a standard for how to define like the difference between, if the FDA has a standard for a definition, because they regulate food, for what constitutes a bread versus a bun or a roll, then the odds are good that somebody from Nist at some point might have been involved in coming up with a standard for measuring the softness of it. And okay, maybe measuring the softness of a bun seems like a rather pointless thing. But you know, if somebody said, well, we need a standard that everyone in the industry can use for measuring the concentration of some kind of polychlorinated hydrocarbon, then somebody from Nist was probably involved in that for coming up with the techniques for measuring the concentration of this and say, here will be the standard method for measuring the concentration of this chlorinated organic compound, which is important for environmental reasons. And there's a lot of money riding on this, whether it's environmental regulations, whether it's having a way for people in the same industry to talk to each other and have a common industry standard. Many industry standards are done by private organizations rather than the government, but the odds are good that someone from Nist was involved, if not in a formal regulatory function, to say we at Nist have decided, but simply because the people at Nist spend a whole lot of time coming up with standard ways to measure things like exactly how strong is this material? How will you measure the concentration of this? And some of it is decided by the government. Sometimes it's the government saying, here is the standard for measuring the concentration of this pollutant. But the result is that Nist has these labs full of experts who might spend their entire career just figuring out the best way to measure the strength, to quantify the strength of a type of fiber or fabric. And the industries might go to them and say, look, we're not asking you to write a rule, but we know you have a scientist in-house who's good at this. So let them spend some of their time advising us. And they might serve on an advisory panel of a professional society. So Nist has a whole bunch of people who will come up with ways to measure things that you would never think of measuring. Somebody at Nist could probably spend hours telling you about ways to measure the aging and quality of paper. Okay? And you know, industry standards matter. You could say this is a silly thing for the government to be involved in regulating, but regulating weights and measures is in the Constitution. And regulating weights and measures is something that, that governments have been doing for millennia. They had scribes, they had all the people who knew how to keep records and do math tended to work for the king or for merchants. They all knew each other. And so these things have been done that way for a very long time. And so even when Nist isn't involved in a regulatory process, they just have giant labs full of people who are good at standardizing measurements. And they will often serve on advisory panels for that purpose alone. Okay, so why is Nist publishing a handbook of mathematical functions? Because along with coming up with ways to measure exactly, I don't know, how strong a type of paper is, in the midst of producing all these different kinds of data, they wind up producing a whole lot of scientific tools. And the people who were, you know, working on solving wave equations to standardize measurements of, say, radio signals or something, or coming up with standard ways to measure radar through fog or whatever, they needed all these mathematical functions. And so Nist compiled these things. And because they're not from the part of the government that's supposed to keep secrets, because they're from the part of the government that's supposed to report to the public, they publish these tables. And once upon a time, every physicist, or at least every physics professor and most physics PhD students had these handbooks of mathematical functions on their shelves. But then Nist decided, you know, there's this thing called the internet, and it's not just a big truck, it's a series of tubes. Let's put it on the internet. And so they actually have one of the best handbooks of mathematical functions. And every fact you could ever want to know about Bessel functions, modified Bessel functions, spherical Bessel functions, or anything even vaguely related to them is in there. If you wanted to know about, instead of Bessel functions, Airy functions, they got a chapter on that. You want to know about Legendre functions and related things, they've got a chapter on that. Whenever I need to know some fact about how to take the second derivative of a weird combination of Bessel functions, the first place I look is the Nist Digital Library of Mathematical Functions. Anyway, Nist is actually a great employer of physicists. And so besides having, you know, there are people who are busy measuring the strength of silk thread or whatever, they've got a lot of very basic physics research labs. Sometimes because it turns out that to actually measure the strength of, well, maybe not silk thread in clothes, but if someone wanted to measure the strength of some microscopic thread used for cutting edge surgery or some nanofiber used in new materials, you need a lot of basic physics and chemistry. In order to standardize the way to characterize materials, they have a neutron scattering facility. So they do a lot of basic physics research there. They will have people just doing very basic research, but they're always encouraged. They're allowed to follow their curiosity to a certain extent, but they're always encouraged along the way to come up with ways to standardize measurements. If somebody at Nist has gotten really into techniques for, I don't know, observing molecular processes inside of a cell, then it's part of their culture that they will also try to standardize the way that you do that and join a and you know, you say that's a bad thing. I mean, some of you are laughing right now, but it's actually not entirely crazy. Imagine if you go to a conference and you go to a conference session and there are 10 people all giving presentations on observing some process in a cell, and they're quantifying it 10 different ways. How do you compare their data? All right. Every new measurement technique. Initially, there's a proliferation. Everybody can and will come up with their own way of measuring it. And that's fun and that's great creativity. And then somebody says, well, how are we going to compare our data with each other? And committees form and standardize it. And there are usually Nist people on those committees. Cryptography. When you standardize, and standardizing cryptography is tremendously important. Otherwise, you couldn't put your credit card number into a web browser and buy something. So cryptography, you'll have a whole bunch of people from the private sector. You'll have a whole bunch of sort of independent consultant hackers who have done this on their own. You'll have people from the NSA who may be there because it is part of their mission to help America protect itself against hackers, or they may be there because it's part of their mission to compromise cryptography techniques so that they can read your email and they can see what you're doing with your credit card number. And then you'll have people from Nist because, you know, people from Nist are really good at coming up with standards. Anyway, it's a great employer for physicists. They have a lot of really smart physicists in lab facilities that are basically like playgrounds. Probably the more fun place to live and work at Nist is their facility in Boulder, Colorado. Probably the bigger, nicer, but not as much fun place to live is Gaithersburg, Maryland. I'm from Milwaukee, so I personally like cold winters, but nobody likes Maryland in August. Any questions about that? And by the way, I actually published a paper with some people from Nist a long time ago. I collaborated with some of them. Any questions on that before we get back to Bessel functions?
Would you recommend that as like a resource for us, or is the stuff a little more complicated in there?
A resource for you is what?
Would you say we should use that for like, or that it's too complicated, some of the stuff in this library?
I'm trying to write the homework sets so that you won't absolutely need it. But if you're curious about these functions that we're studying, by all means, browse through it. There's absolutely no harm in browsing it. A lot of things in this book are stated without proof, which has an obvious downside, but the upside is sometimes you don't care about the 15-step derivation that leads you to a certain thing. You just have a calculation, you've got some Bessel functions, you want to simplify it. And if they can tell you that, hey, this sum of Bessel functions is equal to this much simpler expression, normally I would say don't trust things presented without proof, but this is such a highly reputable source that, yeah, you could go ahead and trust it. And if you really want to know, they list a bibliography. So, you know, this is why they're trustworthy, okay? Other questions? Nist would be a great place to apply for an internship. And I will tell you that the Nist Boulder group and probably the Gaithersburg group too. I know the Nist Boulder group is famous for quantum computing. I do believe that there are some good people there in Gaithersburg simply because I know that Gaithersburg has a good atomic and molecular physics group, but I don't know as much about them. I just know that some of the more famous quantum computing groups are in Boulder. I worked with some of their chemistry people on a paper about some techniques for quantifying cell migration a very long time ago. Okay, back to Mathematica. A more relevant fact is that at large values of x, very far from x equals 0, it turns out that the Bessel functions decay as roughly 1 over square root of x. Okay, more precisely, they decay as I can be square root of 2 over pi divided by square root of x. And if I wanted to really be whenever you plot something on a log scale, you have to take the absolute value because the minus sign. You can't take the logarithm of a negative quantity. They really decay as cosine of x over square root of x times some constants. Right? And there's a phase shift in there. But the important thing is to know that asymptotic form. Now, let's talk about the significance of that. Actually, let's pause. I want to do one other thing. I've been telling you, we'll get to why this asymptotic form matters. Let me just complete the menagerie of Bessel functions. Besides the Bessel functions of the first kind, there are Bessel functions of the second kind. They're the linearly independent solutions, okay? And the linearly independent solutions, these are called Neumann functions. They always blow up at x equals 0. That's inevitable. No matter what type of, no matter what order they are, they always blow up at x equals 0. And it turns out that they blow up as 1 over x to the m. Oops. Let's try that again. So let's plot Bessel y of m. Instead of, and let's divide by x to the minus m. And we're not going to see anything on that scale. So let's just plot what I want you to notice is that y sub m divided by x to the minus m starts off flat, no matter what the value of m is. All right. Whatever the value of m might be, y sub m, except for 0. Let's, you know, this is so different that it's worth putting it on a separate line. For m equals 0, it turns out to blow up as a logarithm. Let's just put that fact in your catalog for now. Okay, right now I'm using these graphs to toss out several facts, and then I'm going to give you the physical interpretations of each of them. So what should you take away? First of all, we established that Bessel functions of the first kind wiggle. So do Bessel functions of the second kind. For small x, Bessel functions of the first kind are approximately x to the m. And Bessel functions of the second kind are approximately x to the minus m, except for m equals 0, which is a very weird special case. The asymptotic form of the Bessel functions of the first kind is cosine x over square root of x with a phase shift. Ditto for Bessel functions of the second kind. Cosine x over square root of x with a phase shift. Technically, I think that one of them is sine and the other is cosine, but then they both get some phase shifts. So facts we're collecting. Now let's talk about the modified Bessel functions. Those are called Km and Im, and K sub m, fine, but I sub m looks a lot like imaginary part of. So Im of x, you're just somehow supposed to know that this is a modified Bessel function of the second kind rather than an imaginary part. All I can say is that anybody who would write down Im of x without making it abundantly clear that they're talking about a very special kind of Bessel function, that person is a terrible writer. So normally there's a whole bunch of prefacing. We're using one of the weirder species from the Bessel function zoo. David Attenborough has gone out into the wilderness to find the rare spotted modified Bessel function of the second kind. All right, there's enough prefacing around that. But what I want you to notice is that the Bessel functions of the second kind, sorry, the modified Bessel functions, they look like they're either blowing up exponentially or decaying exponentially. And there's a reason for that. The reason, let's just confirm that with a log plot. Sure enough, when you plot the logarithm or you plot on a logarithmic scale, the K sub m functions decay linearly. Because remember, the logarithm of an exponential is a straight line. The I sub m functions grow linearly on the log scale because the logarithm of an exponential is a straight line. And it shouldn't be too much of a surprise that one type of function behaves like a sine or cosine, and the other one behaves like an exponential. Because what's the relationship between sinusoids and exponentials?
They're the same thing.
Yeah, the sinusoids are just exponentials with imaginary inputs. And exponentials are just sinusoids with imaginary inputs. So at this point, let me go back and share my other device. And let's try to work out some of this. Fact one, Jm of x is proportional to x to the m for small x. Well, that just really comes from the assumption we made in the beginning. We said that it's got to be x to some power sigma, and then we found that sigma is plus or minus m. So one of them has got to grow, at least for small x, as x to the m, and one of them has got to go as 1 over x to the m. But y sub 0 of x is proportional to ln of x. That one's not as obvious, but this actually shows up a lot in physics. Sometimes you've got a function, a quantity, that if you just proceeded in a very naive way, you'd say, oh, our quantity f should be proportional to x to the 0. Seems logical enough. Except that where this usually comes in is somebody says, all right, df dx. And by the way, this has nothing, this is not just a Bessel function thing. This actually shows up, frankly, more often in statistical mechanics than in wave theory. It shows up sometimes in wave theory. They say, okay, df dx is equal to x to the n. So then f is the integral of x to the n dx is equal to 1 over n plus 1 x to the n plus 1 plus a constant. And that's perfectly sound reasoning in most cases. Does anybody see a case where that might fail?
When n is equal to -1?
Yep. Because then we've got 0 in a denominator. And 0 in a denominator doesn't look any good. But then we've got the integral of x to the -1 dx, which is the integral of dx over x is equal to ln of x plus a constant. So it's often the case that if a very simplistic approach would say, hey, we've got to have x to the 0 here, then a more subtle approach would say, maybe we've got a logarithm. Another way to look at it is that we talked before about degenerate solutions to differential equations. If we had, say, a differential equation with constant coefficients, e to the lambda t is our solution. Actually, let's not do that one. Let's do the Euler equation. If we had ax squared d squared y dx squared plus bx dy dx plus cy equals 0. That should be a y, not an x. Of course, y is equal to x to the n. But if n is degenerate, meaning that it's the solution to a quadratic equation where both roots are the same, then what you actually get is x to the n and x to the n ln of x. And that's what's going on here, okay? If we solve this differential equation for m equals 0, if we solve the Bessel equation for m equals 0, well, m equals 0 is a degenerate root. Now, if we were solving for m equals 2, then there would also be an m equals -2 solution. If we were solving for m equals 7.8, there would also be a -7.8 solution. But when m equals 0, there's only one solution. And so one of those solutions has to have a logarithm in it. It has to blow up logarithmically. Any questions on that? My goal for today is to help you make sense of Bessel functions. You're never going to write down those series. You're always just going to type them into a computer. You know, whenever you need to calculate something with a Bessel function, if you need a number, you're just going to plug it into a computer. With a trig function, you know, you almost never say, okay, I'm going to write down the Taylor series and then plug things in, then get the number the hard way by hand. You always plug it into a computer, but you already have an intuition for what a trig function is all about. Now I want to give you some intuition for why Bessel functions behave that way.
Professor, can you repeat why you circled your x to the n natural log of x?
That's the second solution.
And you're saying that this blows up, correct?
Yeah, ln blows up when x equals 0.
Okay.
For large x, Jm of x is proportional to cosine of x over square root of x. Well, the thing to keep in mind is that these are solutions to the wave equation. Okay, and let's consider a wave in 2D. If I've got a wave spreading out in 2D, it's going out in all directions. If we were to compute the flux, we would be integrating the intensity times r d phi. All right, I can make a better diagram than that. All right, so you'd have flux going out in every direction, but since it's in 2D rather than 3D, the flux is not spreading out over an area, it's spreading out around the edge of a circle. So you just be multiplying the intensity by r d phi, right? And if I've got a source here, I've got some source, something that's emitting light or sound or whatever my wave is, then I better have, unless there's something absorbing, unless there's something that's in some way diminishing the amount of energy passing out, I better have that the flux is the same at all distances from the origin. Or the integrated flux. The flux density, the integrated flux through a surface, it better be independent of R. And in the problem set that I'm writing at the moment, that will be demonstrated for certain solutions, for certain types of Bessel functions. The flux through the surface had better be independent of R, all right? So that means that our intensity had better be proportional to 1 over R. Any questions on that line of reasoning? Well, for most types of waves, the intensity is proportional to the square of the field. For instance, for light waves, it's 1/2 E squared plus 1/2 B squared. And then there's some epsilon naughts and mu naughts and C's, but in grown-up units, those are all 1, okay? And so these fields, these squared fields, had better be proportional to R. So the field had better be proportional to 1 over the square root of R. That way the field squared is proportional to 1 over R. Any questions so far? If we think of Bessel functions as 2D solutions to the wave equation or solutions in cylindrical coordinates, all we're really saying here is that something spreading out in cylindrical coordinates, something spreading out in 2D has to decay as 1 over square root of R, just like something spreading out in 3D has to decay as 1 over R so that the intensity can decay as 1 over R squared, so that the integrated intensity over a sphere, you take the 1 over R squared, you multiply by the R squared area of the sphere, and you get a constant flux. You get the same flux through all surfaces. Then you can say, okay, well, why is it a sinusoid? Why is it that Jm is cosine of it's cosine of x with some phase shift, and Ym is cosine with a different phase shift, or basically one of them is a cosine, one of them is a sine? Well, it's a sinusoidal wave. Okay, we got an oscillating wave spreading out in 3D. Sorry, 2D. And this is why people define Hankel functions. Hm of x equals Jm of x plus I times Ym of x. Because one of these is a shifted cosine and the other is I times a shifted sine, and they both have some complicated phase shift. But basically we've got a cosine time plus I times a sine, this becomes proportional to e to the I x times some constants over square root of x. And strictly speaking, there are two Hankel functions. One of them has a plus here. The other one has a minus there.
And just so that I'm following along, it's proportional to the square root of radical x because we're working with Hankel functions in 2D.
Well, I just argued that the Bessel functions of the first and second kind both have to be proportional to 1 over square root of x, so that a wave, the flux of a wave in 2D, so the energy is conserved by a wave spreading out in 2D. Now, one question you could fairly ask is, okay, fine, but I get why you're defining these things this way, but why would you ever use the solution that blows up? Well, oftentimes we're scattering a wave off of a circle, okay? And if here's the origin. In here, we've just got Jm of x. But out here, and actually, I should be writing this as Jm of k1x, or Jm of k1r, okay? Because if you think way back up there, when we wrote out the wave equation, at the very beginning, we said that we've got a k squared in there, which is omega squared minus kz squared. Okay, well, k, that's a wave number, and it's also going to involve the refractive index. So inside one material, we're going to have one value for the wave number. Out here, we could have Jm of k2r and Ym of k2r. Okay, so in here, Jm doesn't blow up at the origin. Out here, we should have a constant times J1 of k2 r plus another constant, sorry, that should be Jm, another constant times Ym of k2r. And you can say, well, Ym blows up. Yeah, it blows up, but it only blows up at a place where we're not using it. It only blows up at the origin. My origin isn't in this medium. And so this gets done a lot in scattering problems. You use the Ym in regions where it won't blow up. And you don't just use it because you can, you use it because you have to. You use it because in order to have as many variables as you have equations, you need to have two types of functions, so that you can have two coefficients. So you can have two unknowns and two equations. Because usually you wind up having an equation saying that the field is continuous and another equation saying that the derivative is continuous. The more important point is that, generally speaking, when you're trying to solve a complicated problem, your field is going to probably have several pieces. If something is a valid solution to the equation, then you had better allow for the possibility that it's present. Otherwise, you'll have fewer unknowns than you have equations, and things are going to go wrong. Any questions on that? I don't think I'm going to have time in the last 60 seconds to explain modified Bessel functions, but there's actually some really, really important physics that modified Bessel functions work for. It has to do with total internal reflection and the fact that the wave number becomes complex when you have total internal reflection. So next time I will talk about total internal reflection. I'll talk about integrals that represent the Bessel functions. And then we're going to talk about the fact that the Bessel functions are orthogonal to each other, and that writing down these orthogonality relations actually enables you to understand things like vibrations of a circular cylinder. And the modified Bessel functions are used in order to solve the problem of light in a fiber optic cable, which is a rather practical problem that many of you will probably get jobs working on, because a whole lot of physicists get hired to work on optical fiber communication. With that, have a good day, and I'll have my usual office hours.
Thank you, Dr. Small.
Mhm.
Thanks, Dr. Small.
Mhm.
Oh, Dr. Small.
Yeah.
Maybe this isn't a good time to ask because everybody left. On the final, how much is going to be on the new content and how much is going to be reviewed? And like just approximately.
I would say approximately 25% new content.
Okay, thank you, Professor.
Mhm.
Have a good day.
Good.